All right, so it's very similar to last test in format, but I guess like the things that have been added, you need to know like well, the log rules, exponential rules, and trigonometric rules, and then we have this integration by parts, and the log and trigonometric rules for integrals, which is basically the same thing but backwards. And then there's going to be one definite integral, one linearization, a tangent line related to each problem and min-max, area between two curves, and initial value problem. So I guess you get to choose what you want to cover first.
No, I would like to go over linearization.
All right. So linearization is very similar to a tangent line problem in the fact that you use it by solving a tangent line. So let's say we had the function like y equals e to the x, and we want to evaluate this at, let's say, x equals 0.01. Well, that's kind of like impossible to do without a calculator. So it's kind of like what to do if you don't have a calculator. And so essentially what we're going to do is we're going to take, we're going to find a tangent line, as if you think of like what the graph looks like, e to the x looks something like this. And as if you have like a tangent line to a point, the closer you zoom in, like if you could zoom in all the way, when you got really close to the point, it would pretty much be the same line. And so you can kind of use this tangent line and the values for this tangent line to figure out what an x value would be on the actual function. So we simply just start by finding the tangent line. So we need a slope and a point. And so this is kind of where linearization is a little bit different. So we just choose a number that we know that's very similar to this. So
if in this case would be 0.
0, because we know that e to the 0 is what? 1, right? So that would be our point, 0, 1, right?
Right.
And now we take the derivative, and this one's really easy, right? That's a derivative.
Right.
And so then we're going to use that same point, or the 0, for our slope, which means our slope is just going to be 1. So we're going to end up y minus 1 equals 1 times x minus 0. So we're going to basically say y equals x plus 1 is our tangent line. And so now this is where we get to use our x number, because we're just going to plug this value into x. So then that would just be y equals 1.01, right? And it makes sense logically, too, because if you think about it, we know that e to the 0 is 1. So e to something really close to 0 should be really close to 1. And if we took a calculator, we could kind of see it, where if we plug in and we just evaluate e to the 0.1, we'd come out with a very similar answer. Let me just grab my calculator real quick. I can find where I put it. All right.
So correct me if I'm wrong, but up until this last step where we plug in the 0.01, it's just a tangent line problem?
Essentially, yeah.
What would, I mean, essentially, is there any cases where like it wouldn't be?
No, so you're right.
Okay.
So if evaluated, you e to the 0.1, you get like 1.01005.
Yeah.
So we're really close. And so it kind of works as an approximation. But the farther away you get from this number, the less close it will be. So if this was like 0.5, then this would probably be pretty far off, this approximation. Right. Because the farther we get away from the point, the more distance we're going to have between our actual function and our tangent line.
Okay.
All right. So that's kind of covers the definite integral. And usually these problems aren't much harder than this. They're because it's like it's figuring stuff out without a calculator, so it isn't. They aren't crazy hard problems.
Right.
Yeah. Like if you remember, the last test was just like a square root of some function, so it's going to look something like this.
Okay.
All right.
That makes sense.
All right. So I guess, any other things that you specifically want to cover before I just hop into some of the stuff that I got?
I would like to cover like a related rate problem, or maybe like a min-max.
All right.
Just because like with the derivatives and integrals, a lot of the homework is on that, so it's easy for me to get comfortable with that. But more of these, there's less of.
All right. So this one's a fun problem. I like this one. So let's say we have 2 planes. And the one is flying south. Let's say at like 450 miles an hour.
Okay.
And the other plane is flying east at 600 miles per hour. So let's say they leave the same place. So there's an airport here, right? And we have this plane that's flying south, this plane that's flying east. Let's say this is 1,800 miles east of where they started, and this is 1,400 miles south of where they started. Now, I guess
what are those numbers again?
So can you see them?
It's very tiny.
Oh, I'm sharing my screen again. I gotta de-share my screen. All right. All right, that better?
Yeah, thank you.
All right. So, and it's just like, how fast is the distance between the two planes changing at this specific point? I guess would be our question.
Okay.
And so, like, when you're doing related rates problems, it's always really handy to write down all our information. So, let's call this like ds dt. So, how fast is going south over time is equal to 450, because that's our rate, right? And then we can say that like our dE for east dt is equal to 600.
Right.
And what are we looking for? We're looking for this distance. So let's just call that like dt. We want to know how fast our distance is changing, right? So we need to come up with some equation that will relate all these different values, right?
Right.
On this one, it's pretty simple. Sometimes it can be hard, but this one I think we can just use Pythagorean theorem. So we can say that this is our distance, d. So our distance squared is equal to our east squared plus our south squared. That makes sense?
Right.
And then so we can say our d is equal to e squared plus s squared square root. Now, we're looking for dt. So we're just going to simply take the derivative of this. But we got to remember that these are dependent upon time. So our east variable and our south variable, because the planes are changing. So like basically when we're going to take the derivative, we have to do what we do to this like d. So if we just take the derivative of y equals x, it would be dy dx equals 1. But so it's kind of, we treat this as like the y variable where we get this dd dt.
Over dt, right.
And then we're going to treat these variables the same as this, right? So we're going to have to do a chain rule because this is inside a function, right? So we're going to end up with 1/2 times e squared plus s squared to the negative 1/2. And then we have to chain this, right? So we have to multiply this by the inside function. So that's 2e plus 2s. And this is where we have to remember our dE dt plus 2s ds dt. All right. And then it's simply just plugging in our numbers, because we know that at this point our E equals 1800 and our S equals 1400. So
interesting. Okay.
yeah, and so I think, so if we plug all this stuff in, this is going to be quite a problem. So it's going to be 1 over 2 square root 1400 squared plus 1800 squared. And we're going to times that by 2 times 1800 times our rate, 600, plus 2 times 1400 times 450. And get a calculator. So
I got about 822, I think.
all right, so I like when we have big stuff, I kind of like breaking this into little problems. So we have 1 over, I guess if we simplify this, is 4560.7. And we're going to multiply that by 2 times 100. All right, so I got 3,420,000 for this number. And
yeah, it's different.
yeah, you can't remember that the chain rule. So if you just plug it into your order of operations, you might end up multiplying this and then adding this last term. But you got to remember that it's multiplied by the derivative of the inside function. So maybe it's just an order of operation there. But
okay.
All right, so I came out with equals 749.8. Well, so that's how fast the distance between the change is. So in an hour, they will be 750 miles farther apart than they are right now. And that's kind of interesting, because on a problem like this, these are constant. So if we really wanted to, we could probably double check this by saying, well, how far apart are they now, and how far apart are they going to be in an hour? And you could check our work on this problem, and I did. So that's how I checked my work. So yeah, so I'm positive that this is the answer.
Okay. Yeah. No, that makes complete sense.
So does this like make sense about how we did this problem?
Yep. Complete sense. It's just, yeah, it's a little confusing at first to be like, ds over dt, de, dt, dd, dt, and then put them all together in a way that.
Yeah. So yeah, in like related rates, it's important to really identify that our east and our south are changing, so they're dependent upon time. So I guess you could technically say that there's some other function right here. So we kind of treat it as a dependent variable instead of an independent variable. And so when we do this, we have to kind of treat it like a chain rule, where we get this extra thing out at the end.
Right.
So this stuff is important. All right. So I think that does it for this problem.
Yeah, that is a good problem.
All right, and you said you wanted to cover like a minimization or maximization problem?
Yeah.
All right.
Possible.
So let's say we have this spring. I'll draw a spring real quick. And it's attached to this block of wood, right? Let's say like we pull the string back and we let it go and it goes back and forth, right? We can describe that movement by saying, well, let's say their velocity is going to be 6 sine t. So that's what our velocity is going to look like. All right, so this is kind of simple, but it's principle. But so at what time is it going to be moving the fastest, and how fast will it be moving? Right?
Right.
So to start this problem, minimization.
I didn't like these spring problems because I wouldn't do it the right way. I just do the physics way. And so I wouldn't be using the methodology. I'd just be like, oh, I know this.
Yeah. It's really easy to do that because I think that, there are definitely times in this class where you could solve it with some other way. But so a maximum minimization problem, we always just have to remember that we're going to be setting a derivative equal to 0 somewhere in here. So we're just basically going to take the derivative of this and set it equal to 0. And so this part,
that tells us that
it's kind of like, since the derivative tells us like our slope, if we think about a sine function like this, if we take a slope, if the slope is 0,
right,
we're gonna actually, and let's say that it runs from 0 t to 2 pi. The time goes from 0 to 2 pi. It's kind of a weird way to keep track of time. Because if not, then this technically goes for infinity, right? So when we take a derivative and we find where the slope equals 0, we're going to be at a place where it's at a min or max. And
we won't know what's what from just finding those points, right?
You could kind of guess on this one since we know what a sine curve looks like. But in general, you kind of have to like go through the whole find the critical points and test them and see them in the function where they are. So, so if we take the derivative of this, we get our dv dt is going to be equal to 6 cosine t. So this one's pretty simple, right? Then we just set this equal to 0 cosine t. And so where does this function equal 0? Well, this is where knowing your unit circle can be handy, because we know that cosine is going to equal 0 at pi halves and at 3 pi halves. So if you think about the unit circle, we have a circle, right? And cosine at 0 equals 1. So, and every half of a pi, so this would be pi halves, cosine is going to be 0, and at pi, it's going to be 1. At 3 pi halves, it's going to be 0 again. And so now this is where it's kind of handy to know the sine of the curve, right? So know what a sine curve looks like, because we already know that this is the pi halves and this is the 3 pi halves. And if we were asking for like let's say speed, then it wouldn't really matter because the speed is the absolute value of velocity. But if asked where the velocity is the greatest, I guess this is a -1 and this is going to be a 1. So for our t is going to equal this pi halves or our 3 pi halves. And I think in this context, either of them would work. And now we want to know how fast our spring is moving at this point in time. Well, we just plug it back into our original equation, and we know that the sign is going to be 1 and -1. So at pi halves, so the velocity at pi halves is going to be 6, where the velocity at 3 pi halves is going to be a -6. And who knows what units those are in, because we didn't specify any, but
just 6 speed.
It's 6 speed, yeah. It's a bike, but so I guess that's kind of a min and a max problem.
Okay.
I was hoping I could find a more complicated problem, but it kind of works. So it's the same process. When we're working a min max problem, we're always going to set something equal to 0. All the function we want to minimize, we got to set equal to 0. And so sometimes you have to like figure out kind of like in a related age problem where you have multiple equations to get rid of one variable. So when you take the derivative, you don't have extra stuff floating around.
Okay. So if it were to say, when is the acceleration the greatest? How would we approach that?
When is the acceleration greatest? Well,
Right.
What is acceleration?
Change in speed.
It's the derivative of, I guess, our velocity. I guess actually this should be a position function. If this is position, let's say that this describes our. So I guess that's kind of actually what we did, is acceleration, because we started with velocity. But essentially, you just basically do it a step farther. It asks you to find where the acceleration is the greatest. Then you would once again, you would find the derivative and then set the derivative equal to 0 and test the points in your function to see how fast it would actually be moving.
So with min max, like we would just always set the derivative to 0. There's never.
Yeah. So if you're working with a min max problem, you're always going to be setting something equal to 0.
Okay.
You're always going to find some function and say, I need to maximize this function, so I want to find where the slope is equal to 0 or where it's not moving, because if it's not moving, then it's got to be changing directions.
That makes complete sense.
But sometimes it doesn't have to be changing directions. Sometimes you got a function that looks like this, where it will like be going up. It's called point of inflection, where the slope is technically equal to 0, but it's not a min or a max. And so that's why it's sometimes confusing. So sometimes you can get like points out that are neither. And so that's kind of important why you test your points that you get. Because these are critical points, but they're not necessarily min or max values. So in this case, both of them, one's a min and one's a max. But in some cases, you'll get one that's, I don't know, flexion point, where it changes from a negative to a positive, but is not either a min or max.
Okay.
Right. So I guess. So I guess one of the things that I wanted to cover is a tablature method problem. I don't know if you guys have talked about this or not, but let's say we have like the integral of sine x e to the x dx. Have you done stuff like this before?
Yeah.
So you know about because if you just do normal tablature methods,
This is going to go forever.
Ever, right? So the way you solve it is you simply just say u and v, or dv. What? All right. Yeah, so then you basically just set up your problem, and then this like straight across bar that we do is another integral. So how you go down like this, that means it's just simply a turn. So that would be like sine e to the x, sine x e to the x, and then that would be minus cosine x e to the x. And then we get here and we get this minus this integral of sine to the x, e to the x dx. And then we can basically just say that.
Wait, one second. Wouldn't it be plus cosine x e to the x because the derivative of? Oh wait.
Well, if we did it the other way, I could see how you could get that. But the derivative, so this is because it goes like positive, negative.
Okay, so yeah, because okay.
Yeah, and then we just simply, so this is technically a plus, a minus sign in here, but we just move the negative outside of our integral. And then we say that, well, this is equal to our integral of sine x e to the x dx. And then we can just say, well, this term and this term are the same, so we're going to combine them. We're going to say we have 2 of this and get rid of this.
Wait, wasn't one of them negative? So.
Well, we moved the negative out. So we had this plus a negative sine x e to the x dx.
Right.
But we can just say this is a -1, right? Out front of the sign. And so we just treat it as a constant. We pull it out. And so instead of this being positive, we put the negative out here and get rid of this negative on the inside.
Okay.
And then we add this over and basically get rid of this term completely. And so we have 2 here. And then we simply just divide by 2. So we would have the integral of sine of x e to the x dx is equal to sine x e to the x minus cosine x e to the x all over 2. And that's our integral.
Boom.
Yeah, don't forget plus c at the end. You'll miss infinite points for that one. This is an infinite number of answers right here, right? So it's kind of like a weird way of going about it. But I guess this is sometimes kind of hard to see. Like a couple other things about integration by parts. If you have an ln of anything in your, like an L of an x, you're always going to treat this as our u. That's always going to be u. And
ln of something is always u.
So if you're doing like integration by parts on a problem and there's an ln in there, that's always got to be declared your u, because it's like, how do you, like, if it's your dv, it's like, well, ln x squared, like it's weird. So that's handy to know that this ln u, if you have this ln x in your equation and you're using integration by parts, always the u. And sometimes like you'll end up having to like evaluate integrals at the end. So kind of like how we did this integral here, how we wrote this integral out. Lots of times in like ln problems, you'll have to end up doing the integral at the end. Like, but instead of something like this, it will be something you can evaluate. So those are a couple of things to watch out when you're doing the tab method. I guess that's all. I guess the initial value problems are kind of fun. So maybe we'll do that one. And unless you have like any questions on basic rules, maybe we could cover just simple basic rules real quick.
Yeah, I was actually going to say that was the one question before we finish I'd like to go over as well.
Just basic rules. All right. So let's say a TV show has a bunch of people watching and it just started. And so the number of new viewers can be described by a function like this. So the rate at which new viewers are coming, so this would be technically v prime t, is equal to 900 e to the 0.3 t minus 4. So the rate of which our viewers is increasing looks like this. And I guess just the question is how long is it going to take for us to reach 1 million viewers on our show if at the 1 million viewers, let's say that this is in thousands, that this comes out in thousands. So let's say that V0 equals 100, or that's in thousands. So it would be 100,000 viewers. So it starts off with 100,000 viewers. How long is it going to take until we get to a million viewers, or V equals 1,000? I guess it would be. And to start this problem, what we got to recognize, well, we got a function that describes how fast it's changing, and we want a function that describes the complete number. And so we're just going to take the integral of this, right?
Right.
900e to 0.3t minus 4.
And the 900's constant, so we can move that out.
You just pull the 900 out. And this is a very simple u substitution problem. You just say u is equal to 0.3t minus 4. du is equal to 0.3 dt. So then we got to pull the 0.3 out, like we got, so we can substitute out this dt for this du. So if we rewrite this, we end up with, and then we're going to pull this 0.3 out. Does it make sense what we're going to do for this next step?
Yep.
All right. So we're going to get 900 divided by 0.3 integral of e to the u du. And then this is really simple. It's just e to the u. So 900 over 0.3 e to the u. And then we have to plug back in our du, which is our 0.3t minus 4. And that's in the exponent, sorry. And that's plus c, and that's equal to our VT, our how many viewers we actually have. So this is where we use our initial value that we have, that at 0 equals 100. So we're just going to plug 0 in for t. All right. So we get, so this equals 100 equals, I think this comes out to be like, what, 3,000?
3,000, or since we're doing it in thousands, so 3.
Well, we'll leave this as a constant. So I think, so this is, we're going to say that as 300, 3,000. So, and then we'll say e, this ends up being e to the, I think, so we want to solve for our c. So this is 0. So it's e to the negative 4 and plus c. So
by 3,000, so 55 equals 100. So c is equal to 45.
Yes. Yeah, and so you just have to take the ln of this number and then add 4, then that will equal our c. And you said that came out to be about what?
45. C equals 45.
Roughly equal to 45. It's probably one thing. And then we're going to use the c value, and we're going to plug it back in for the c up here. And then we're going to say at what time or what t does this equal 1,000? So now that we figured this stuff out, we're going to solve this for our t. So we're going to minus this 45 over and divide by this 3,000. So we're going to get 1,000 minus 45 over 3,000 equals e to 0.3t minus 4. You're faster on the calculator, so what does this come out to be?
Let's see, now you put me on the spot. 0.318.
All right.
We take the natural log of that.
Yep. To get rid of this e.
And so it'd be 0.3t minus 4.
Yep. And then we divide across by the 0.3 and add 4.
5.
What did you get?
9.5.
And I think that is right. So that comes out to equal 9.5. And let's say that's weeks. So it takes 9.5 weeks from when the show started with 100,000 viewers to get 1 million viewers.
So an initial value problem, essentially all you're doing is doing the derivative, finding C, and then using that to then calculate for a specific time.
Yeah, in this problem, sometimes initial value problems will be like if we dropped a rock off a building. Sometimes sometimes it usually has a time element in there, but it doesn't have to be time. So
okay.
Yeah, but it's finding it has this initial point, so it's finding the integral, which we did, and then using the point to evaluate to find that C value, which is what we found was equal to about 45, and then using that for whatever other information. Sometimes they just want what's the function that describes our thing, and so this one we went a little bit farther than some problems might have you go. They might just ask for the equation in which we would end at this step, but all right. So yes, we can just cover some basic rules, and then I think that should be it.
Awesome.
So, yes, I guess the new stuff that we haven't on this test is like e to the x. Actually, we'll put u's here. We have e to the u, a to the u, ln of u, and then we have the sine, cosine, cotangent, tangent, cosecant, and secant. So this is the stuff that's new on the test derivative wise, and it's important to always remember that these are always going to have like an inside function, so they're always going to be ending up with the chain rule. Is the screen still right? Can you still see it, or did it?
Yep.
All right. So e to the u is simply e to the u prime. So there's this chain rule out here, and that's something that's similar to everything, is there's always going to be a chain rule associated with these. So this a to the u is a little bit different. So when we take the derivative of a to the u, it's going to be a to the u ln a times u prime. So it's like the e to u, but there's this ln a function in our thing.
A being
a constant. So if it was like 7 to the 4t plus 3. So if we have something like it could even just be like 7 to the x.
Okay.
And
so
then
case,
yeah, so you want to solve it? I think you can.
So it should just be 7x times ln of 7 times 7 to the x.
U prime. What's our u?
Prime. Oh yeah, sorry. Yeah, it should just be 1.
Oh, if this was a negative. 7 to the negative.
In which case, it would be -1.
Yeah, it would make this whole thing negative, right? So
right.
I think it's sometimes really easy to lose track of that negative if we have something like 7 times like 4 minus x. Sometimes it's really easy to lose sight. Oh, that this is it's a negative x, and
right.
So that's always kind of important to remember that if you have a minus x, it's going to come out as a -1 in your derivative.
Keep it in there.
So ln u, I guess the derivative of ln u is always going to be 1 over u prime. So
isn't it absolute value of u?
That's if we're doing the integral. So if we do the integral, if we do the integral of 1 over u, it comes out to be ln absolute value u. And yes, you're right. Don't forget the absolute value. They'll take away points. So yes, so that's kind of important to remember that if you're taking the integral of ln u, then it's going to come out as with the absolute value sign.
Okay.
And then the sine u is simply cosine u prime. And then cosine u is negative sine u prime. And then cotangent is going to be negative cosecant squared u prime. So you're always going to have this chain rule because these all have an inside function.
Right.
And so it's easy to treat if this was just an x to forget that there's technically a multiple of 1 out there. So it's always important to remember that stuff. And then tangent would be secant squared u prime. And cosecant is going to be negative cosecant u cotangent u prime. And then our secant is going to be secant u tangent u prime. And so those are all of the basic rules. So the trig functions, so like there's some derivative rules like the power and quotient rule that don't work backwards. These do. So these go either way. So if you said what's the integral of cosine, you could say, oh, it's sine. So they kind of just go back and forth. But
Okay.
stuff like this, a little bit harder to just go straight backwards because there's this ln a thing that gets multiplied out there. So
Right.
I guess that's the new rules that are covered and this test. So I guess if there's any other questions, I think we can call it, right?
Yeah, just one quick question. For finding the area, if you have essentially, because normally it's just top minus the bottom, taking the derivatives and what have you. And if it's left and right, essentially it's left minus right.
Yeah. All right. So I think I understand what you're saying. Okay, I'll draw a picture. So if we have, so you're saying that a lot of problems, we have a curve like this, and it gives us x values, and it says what's the area like this, and so you just do top minus bottom, right? But you're saying what happens if we have two functions and they look something like this, right?
Right.
And they want this area right here.
Because for the one, it was interesting. They did it twice. They did for the whole larger, the one that slopes from left to right downwards. They did the whole thing and then subtracted. See, I'm not even quite sure how they did it.
All right. So let's say like they want this area, and so say they want this area, right?
Okay.
So you're right, where if we tried to take the integral of top minus bottom, what are we going to hit? Well, we're going to run into this problem where top minus bottom, it's the same function, right?
Right.
And so, yeah, you could do it where you could change it. So this would be like y equals. You could change it and say x equals, and then take the integral of this curve minus this curve, and you could do it that way, right? Or you could simply turn this into two problems. Like, I don't know if this one would, I think this one might be kind of hard to turn into this problem. If the graph looked like this, you couldn't do that. But let's say we had something like this. And if we wanted, we could say, and it wants this area, well, we could simply say, well, we're going to split it right down this middle, right? And then we're going to take the integral of this curve minus the bottom, and we're going to add it to the integral of this curve minus the bottom curve. That makes sense? So you could do it this way, where you switched the coordinates from y equals to x equals something. Or you could identify a place in the middle where it would still work on either side, and then do it as two separate problems. That makes sense?
Yeah. So for the one on the right, you would say that the bottom is just x equals 0 for this example.
Yeah. So we just say that x equals 0 on this example, and then it's not that hard of a
So
problem.
how do you find that middle section?
So if we set two equations together, so if we set like 3x plus 7 equals y, and
okay.
4x plus 3 equals y, you set them equal to each other, and then that will tell you where the x values are the same. So if you really need to find that point, then you set the problem equal to each other. And the same goes for like if we were working with this problem. If we wanted to know the bounds of integration, so let's say we swapped it to the x equals y thing, we still need to know this point and this point, right? We need to know y values. So when we set up our integral, we have the bounds. So we have this a to b, right? Or this a to b integral. So even then, you set the problems equal to each other and solve for x, or solve for the values. And so if you just set the equations equal to each other and solve for the variable, it should give you the points where they intersect.
Okay.
Yeah.
Awesome. Thank you.
Yeah. So, is there anything else, or is that about it?
I think I'm good.
All right. Well, thanks for coming. The one and only.
Well, thank you for holding it. I appreciate it.